So gears, immensely useful things. I mean, they're able to transmit power and they're able to change the relationship of speed to torque. So you find them, of course, absolutely everywhere. And people tell me they have a bit of a problem understanding gear ratios. To be honest, it's not that difficult. Here we've got two gears, and for argument's sake, let's say they're the same size. If I put them together and I give that one full turn, that will turn one full turn. Why? They're the same size. If they're the same size, then the two edges meet and the travel distance is the same, and so they must travel the same distance, and one full turn must equal one full turn, because the distances they travel are the same. Of course, you can expand on that, and that one is actually 2.5 times the size of that one. So if I put this back in place, if I can, there we go, and I turn this one full turn, this one will turn the same distance around the circumference. So this will turn part of a turn. Now this is 2.5 times bigger than this. So if I turn this one full turn, this must travel 2.5 times as far because of the distance around the circumferences. And that is the basis of gear ratios. If the gears have the same circumference, the ratio is 1 to 1. One turn equals one turn. If the circumference is 2.5 times, let's say 2 times for convenience, twice as big as this, one full turn of this will turn that 2 times. One turn of this will equally turn that half. Or if you like, we'll need 2 turns of this to turn that once. Now, it's not the actual circumference of the circle, it's the circumference of the imaginary circle called the pitch diameter, because the teeth jut up into the gear a little bit and jut down into the other gear a little bit, and there's a point at which they meet, and that's the pitch circle. So as long as we can remember that it's just the distance that we're talking about, gear ratios become pretty trivial, really, because if that's twice as big as that, the ratio is twice as big, because the effect it has is it doubles the speed and halves the torque, or doubles the torque and halves the speed, because it's done in the same 2-to-1 relationship as it must be. This is all just straightforward mathematics that I contend isn't that complicated, but it is really interesting. Now, gears, of course, have teeth on them, so what we do is we take a shorthand and we say it's the number of teeth, because the number of teeth is related to the pitch circle. So if this has 10 teeth and this has 20 teeth, there are 2 times as many teeth, and because there are 2 times, it's a 2-to-1 ratio. It also depends on which one is driving and which one is being driven. So if this is driving, it's 2, and this is driven, it's 1. So the drive to driven ratio is 2-to-1. Equally, if this one is driving, this is being driven, and the drive to driven ratio is 1-to-1/2. And so we can quickly get hold of what gear ratios mean. Now, for a very, very long time, that was held to be absolutely true. If you had 2 gears with the same number of teeth, you would get a 1-to-1 ratio. But that actually isn't strictly true. You can get gears to change reduction ratio even if they're the same size. So I do this up in Tinkercad, and it will do what was thought of for, well, decades, if not centuries, as absolutely impossible. We can get a gear reduction from this even though the 2 gears are absolutely the same size. So let's print that off and put that together. Right, let's put this together. The first bit is this tiny peg and it goes in that way around, and it should be a tight fit, so drive it in. When that's done, take this one and it goes on there with a little bit of glue, because that shouldn't be able to turn in relation to that. Now we take these arms and then just clip onto there, and they should be free to swing. Like that. We take the stand and this gear, and it goes in through there and should be free to turn. The next thing to do is take one of these clips and put it on there like that, and then the handle goes on there like that, so we can turn that whole thing. Then we take the longer peg and drive it in there, and again it should be a tight fit. Long peg then feeds through there like that, and then we put a clip on the back of it. So when that's on, you lower that into position above there, and then that will line up with that hole there like that. And we put that peg through the first one where it should be free to turn, and through the second one where it'll be a tight fit. When we've done that, it gets its final clip over that one there. So that's it completed. Right, we've put a dot on there and we'll use the handle as a registration on there. So when we turn that handle one full turn, something curious will happen. So we've turned it one full turn. That has only turned half a turn. So what we've got here is a ratio of 2 to 1. And even though we're using gears of exactly the same size, we've got a reduction ratio because of this. So that I thought was an interesting mechanism because it does something that was thought impossible. Here we have two gears of the same size where it should be a 1-to-1 output, and it isn't. This is in half because of this bar, of course, but we have two gears of the same size in direct contact, changing the ratio that was always thought to be 1-to-1. I think that's really quite interesting, even though that mechanism is surprisingly simple. Now, the quick amongst you will have also noticed it's done something else. This ratio has been transmitted on this axle and this axle. So it's actually halved the output on two axles. It's split the power without having to do anything else. I thought that was just fascinating. What we're going to do is we're going to use gears identical size and bevel gears, 3 of them, to achieve the same thing. We're going to get a change in gear ratio even though all the gears are the same size. Now to do that, what I've done is drawn this up in Tinkercad, and of course we need to print it out and assemble it. Here are the parts printed off. Right, first things first, we've got a plate here with a fixed bevel gear on it. Note all the bevel gears are the same size. And then we have these support pillars. The support pillars hold the frame and they go in one in each of those holes. And they'll be a tight fit, so force them in. Right, once they're in, we take this bevel gear and put it that way around, and there's a clip to go on there, and then that goes in there, and there's a clip to go on there. Once the clips are in place, the handle can go on there, and that should be free to rotate around. We take our final bevel gear and this axle. This axle has two sides. It's a long side and a short side. The long side gets forced in there, and again, it'll be tight, so force it in. Once it's in on this plate, it feeds through there, and there's a clip to hold it in place. Once that's in place, it should be free to turn. That then goes on those 4 points there, making sure that it engages with that gear here. And that's it together. Again, I've put a dot on here because I can use the handle as its own reference point. If I turn the handle once, watch that dot. Half a turn, 1 turn. So we get a 2-to-1 gear ratio out of nothing but gears that are the same size. So with this one, it doesn't matter actually which way I turn it. I turn that way and then I get 1 turn, 2 turns. Turn it that way, then I get 1 turn, half a turn. So it's back drivable, it doesn't really matter. But it is pretty cool, even just as a fidget toy. So of course I will put this onto Thingiverse should anybody be interested in it and want to work with it a little bit more. But we've now created 2 mechanisms that defy that old adage that a 1-to-1 gear can only give a 1-to-1 ratio. Turns out that's just not true. And of course, having a fixed gear ratio like that is cool, but you have to ask yourself the question, could we use basically the same setup to get a different gear ratio? And of course, the answer is yes, otherwise I wouldn't be making this video. And in order to do that, we need another module on there. So I, of course, went to Tinkercad and drew up this. All we've got to do with that now is print it, put it together, and see if it works. So here are the parts printed out, and we start with that part and that part. That shoves in there like that. A bit of glue on there will help that to hold. Then that goes through the centre of that large one there, and that goes on the other side like that. So what we get is a free spinning bevel gear on both sides of this plate. Then we take this long bent arm, that goes through the centre like that, this sleeve goes on there, and then this goes onto there. But that gets glued onto there, but you need to make sure that that's still free spinning and that's still free spinning. We have this axle. It's got a long side and a short side. The short side gets shoved in there because that's actually the drive, and it shoves in that way. So you shove that in there. When that's in there, it goes in this part here like that. And I've put a clip in there to keep it into place. And when we turn that, everything turns nice and freely. Now, we need to put the bottom plate on. To put the bottom plate on, we use these. There are 8 of these, again, with a long end and a short end. And the short end goes in there like that. And it will be a tight fit, so you might need to force it in there or put a bit of glue in there to hold it in place. But the 4 of those go in there like that. Right, when we've done that, we can put the bottom plate on, which lines up with all the holes, and then we can put the handle on here. So that's one module finished. Now we can take this second bevel gear with the medium-sized hole, slide it on there. There's a clip to hold it in place, and then we can put those in place, and they go in place with the short bit facing the bottom. Right, it's nearly done. Now what we do is take this final plate here and the final bevel gear, and the bevel gear goes on the plate that way around, and we stuff this axle in place. And again, the axle's got a long bit and a short bit, and the short bit is the bit that goes through there and into the bevel gear. And once you put it in the bevel gear, there's a clip to hold it in place. And when that's done, it fits on the top there, making sure that the gears engage. So what does it do? Well, I've put a handle on, and I've put a dot on right there that we can watch. As we turn the handle, we get 1 turn, 2 turns, 3 turns. So we get 3 turns of that for 1 turn of that. So now instead of being 2 to 1, it's 3 to 1. And of course it is back drivable. So if we turn that, we get that with 1/3 of the output. That's awesome. Okay, so we've gone from 2 to 1 to 3 to 1 by adding a module, and it does beg the question, how far could you go with it? So we've done a fair bit with bevel gears using that rotation. Now the original one we did was this one, which was with spur gears, and we used this lever arm to actually get that effect. Of course, the next question is, can we get rid of that lever arm, and can we use just spur gears to achieve this reduction in the same way that we just used bevel gears? Now, if we use a structure like this, where we've actually got a rotating cage that goes around that gear, then the answer is absolutely yes. And we need to print that off and assemble it so that we can check that it will in fact do that job. So here are the parts printed off. And the first job is to take the bottom of the cage, which is this bit with the sticky up axles, and take this bit and glue it so that that goes in there and it protrudes 1 millimeter. Now that bit is going to be the bit that we drive. Then we need to take this. This will in effect be a fixed gear. To have that gear fixed, we need to put an axle in it there, and we'll fix the axle and fix the gear to the axle, which will in effect make that a fixed gear. So we need to push the axle through that. But the axle also needs to go all the way down there, plus an extra 6 millimeters. Now all I did to do that was pop it on there and drive it all the way through, and then this will be 6 millimeters deep, so on there and drive it to the bottom, and you'll have that in the correct position. That then slots in here. Then we have our idle gear. The first idle gear goes on that way. The second idle gear, you turn the other way around and it goes on that way like that. And then we have our output gear, which is this one here, and that slides on there and engages with the second idle gear like that. Then what we do is that way around, pop the top on the cage. Okay, remember this one is fixed, so if we hold that, and that's driving the cage, and drive the cage, it goes nicely round with that effectively a fixed gear. In order to do that, we need some supports, so that support goes on here, and then we have a drive gear, which is this slightly larger drive gear, and that goes on there like that. Then this support goes on here, which is nice and loose, and we have an output gear which goes on there like that. So we assemble those, we can drive this, and it will to output on this. That whole assembly then goes on the base on these inner 2 lines, right there. Now we need to fix that axle, which effectively fixes that gear, and for that we use these supports which go on there and there, and they'll be a tough press fit, but you might want to put a bit of glue on them to hold them in place. Right, I've put a dot on there and a dot on there, and that's our input gear. So as we turn that, where is it? There you go. That dot turns much faster. So let me give that half a turn. And you will notice that that dot has done one full turn. And by the time we get that back, then the dot is back into its place. So this turns once, that turns twice. And of course it is back drivable. So if I turn that, you can see how much slower that one is going. And it's going in a ratio of 2 to 1. So, this may be a question of, little thoughts, little minds, little pants, little behinds, but I'm finding this absolutely fascinating. So this is an ellipsograph. It's also commonly known as the trammel of Archimedes, or the do-nothing machine, or the smoke grinder. It's thought to do nothing, but as you move this around, of course these two slides move in the channels, and this draws an ellipse, hence the name ellipsograph. However, the pivot between the 2 points in fact moves in a circular motion in the same way as a 2C couple. So something like that has got to be quite fascinating to somebody like me, because we've been making those kind of things. And of course, we've been looking at impossible gears, and it occurred to me that the trammel of Archimedes might make a fascinating little addition to this idea of an impossible gear to get different gear ratios from gears that are the same size. So I thought I would use this in a gear mechanism, but not quite like this, because here of course the two trammels, well, they cross over each other, and there's no difference if I have it like that, where the trammels are on the both sides, or I have it like this, where I have the trammels on the opposite sides. That is also the heart of an ellipsograph, and I thought that could be used in a gear mechanism. So of course I turned to Tinkercad and drew up this drawing showing what I'm actually thinking. Now of course these bits will be available on Thingiverse should you want to actually download this and play with it. What we're going to do obviously is print that off and build it. And when we printed it off, these are the bits. Okay, let's start with this slide here. That slide gets this axle. The axle drives in with the long piece driving in there like that. And it'll be a tight fit, but drive it in. When you've done that, check it out, put it in there and just make sure it slides freely backwards and forwards. Then we take these bits. There's a deep cog with a diamond hole, and then there's an arm with a diamond peg, and the diamond peg fits in the diamond hole. And that slots on there like that. And we have two gears like this, so take one of those and the second axle, and again drive that axle in there at the long side facing into the gear. That fits into this hole here. And then we can put a clip to hold it in place, and the handle goes on there. The long axle gets shoved down the centre there with that riding on top of it, and then on top of that long axle goes this gear, and this gear will effectively be fixed. Now as I say, they're all stiff, so force them on. This one with the actual slide guide in gets this axle which goes in there. That then drops in here and has a clip put on it, so that it's like that. Now when we turn this handle, this one will rotate around. And remember, these are all the same size, so there is no gear reduction in this at the moment because all the gears are the same size, and that's free to rotate in that direction. Now in these 6 holes around the rim here, we have 6 of these pegs. They get forced into there. Now we take our trammel of Archimedes, and that slides in on that gear, and then this slides in on there like that, and then we can put this on the top of it. And there it is put together. Now, it is particularly Heath Robinson, I'll give you that, but it is a impossible gear done with a trammel of Archimedes, which I just couldn't resist doing, eh? So our usual trick, I've put a dot on there. We'll give it a close-up, turn that handle once, and see how many turns we get out of that. Half a turn, one turn. So okay, that is cool, hey? So it's a 2-to-1 ratio. I will, of course, put these files on Thingiverse, should anybody be interested in them. I did it because it's kind of summing up the week of Impossible Gears, where we're getting a gear ratio reduction or increase, depending on which way we drive it, even though the gears are the same. And the Tremolo of Archimedes worked absolutely beautiful, although I do admit I sprayed it with quite a lot of silicone oil to make it slip. Of course, we spent the week also looking at Impossible Gears, and we did 5 videos of arrangements of Impossible Gears, and people have been coming up with ideas of how it might work. And actually, once you get your head around it, it's pretty straightforward. There's a couple of things that we need to think about in order to grasp what's actually going on. Now, when we have 2 gears that are set at a fixed distance apart and they're the same size, we can think of them as 2 circles. And of course, these 2 circles rotate with one rubbing on the other, and because it's rubbing, or the teeth are engaging, it forces the other gear to move. If they're the same size and set the same distance apart, of course, that gear ratio is 1-to-1. Now, that's one way to look at them. Another way we can look at it is we can think of it as a point on the circle. When that point on the circle is a fixed distance from the centre, that of course is the radius. As the point moves, it's immediately followed by another point. And infinitesimally huge number of points are what makes up a circle, but the important thing is to think of that point. As that point moves, of course, it's going to describe a circle because it's a fixed distance from the radius, and every other point that follows it will do exactly the same thing. Now, these are the ideas of calculus, believe it or not. What calculus does is reduces things to infinitesimally small points and analyzes the movement of the point. Actually, there's an argument, of course, who came up with calculus, but one of the guys, Leibniz, had this concept, a philosophical concept he called the monad. A monad was a particle of reality that had no extension in space, and was very similar to what we're thinking about. We're thinking about a point as it moves. Now, if those 2 circles are held rigidly, apart from being able to move within a relation to each other, that is, the 2 centres are set, then those points that follow always describe a circle. And at some point or other, those points touch each other, and as long as they're touching, they can push and create a gear. Now, what happens if we allow one of those centres to move around the other centre? Of course, what it'll do is describe a circle, and it'll describe a bigger circle. That bigger circle, because everything is the same size, will be twice the circle that the smaller circle is. So, of course, it must move twice as far. That ability to move twice as far is where Impossible Gears work. But, of course, it's a question then of what happens to the point. If we follow the point on the circle, because it's now rotating around another circle, it no longer draws a circle. What it actually does is draws an epicycloid. Now you have to remember, one point is followed immediately by another point, and so they can push, and so we can get a gear. But each of those points forms a lobe of an epicycloid as it travels around the second centre, the centre where the circle is fixed to. As it travels around, it draws an epicycloid. The length of the epicycloid curve is directly the same as the circumference it would have drawn had it been fixed. So now, it satisfies both conditions. Because the centre is rotating around the smaller circle, it must move twice the distance. Because the point on the circle and every other point on the circle is now moving in an epicycloid, the length of the epicycloid curve is equal to the circumference that it would otherwise have drawn. Now, I can appreciate that's a little tough to get your head around, so here are 2 gears of the same size. Imagine that tooth has a point on it. We put them together like that. The 2 centres are fixed so the gears can move around them. As this gear moves, of course, that point moves around like that. As that point moves around like that, it draws a circle. But because it's meshed with this one, it's forcing this one to move around like that. And of course, that point is now driving another circle, and so it's drawing 2 identical circles as this one is being rotated. Now, let's have a look at the case where we fix that one, but this one is now able to move around here. then because this is moving around here, this center is drawing a bigger circle, and so it has to move further in order to cover that distance. Because it moves further, of course, we get an increase in the amount that it moves. However, this point now is no longer describing the circle that we see on the gear. It's describing the epicycloid as it moves around there. And so it's able to satisfy two conditions. It's able to move in a bigger circle, and this epicycloid that's being drawn is the same as the circumference of that little circle, and so everything is super brill, hunky-dory, ace, and satisfied within this geometric construction that we have. Now, if we have a look at one of the examples, then the drive, which is here, is actually in the center of that circle. But of course, it's driving the edge of this circle from here, which is outputting here. So it is in fact outputting on the larger circle. So this arrangement is just to get it to do that, and all of them did exactly that. The drive is on the smaller circle. Because it's pinioned further apart, it draws a larger circle, and the output is taken from that larger circle using various mechanical arrangements that we explored through the week. So we already know if they're the same size, the number of times it'll roll around is twice. But what if it's the general case? Well, let's have the rolling circle to be circle A and the fixed circle to be circle B. Then the radius of circle B is going to be some value, n, so 1, 2, 3, 4, 5, whatever it is. In our case, of course, it was 1. The radius of the rolling circle is 1 over n, so 1 over 1 is 1. And now the answer, how many times, how many lobes will it draw? Well, it will draw n plus 1 lobes. So in our case, of course, they were the same. So we got 1 and 1. 1 and 1 gives us 2, 1 plus 1. That is the same idea that epicycloids work on, and that's really why they work. It's also related to planetary gear systems. They have the same relationships. So the impossible gear works because one circle it's able to roll around another circle, and it draws more lobes because the distance the point travels, and hence every other point, is no longer a circle, it's now an epicycloid. Anyway, I hope that explained it. Thank you very much for watching. I hope you did enjoy the 5 days of impossible gears, because they are a very interesting thing to think about when you think that if you have one set of circumstances, you get one result. Change only one thing and you'll get a very different result. I hope you enjoyed the videos. Thank you very much for watching, and please do remember to like and subscribe.